7 a.m. Boulder time. I think we should get started. I'm Jiang Zhu, host for today's CGD seminar. Thank you very much for joining, and thank you for people who are watching on YouTube as well. I'm really glad to introduce Ofer Shamir today. Ofer comes to us from current Institute of Mathematical Sciences at New York University. Ofer's research consists of both global scale and tropical dynamics, and is characterized by equipartition between theory, modeling, and observations. Ofer's recently worked as a postdoc on the Data Wave project, which is part of the Virtual Earth Systems Research Institute, VESRI, at Schmidt Sciences. He worked to improve the representation of gravity waves in climate models using data-driven methods. The title of today's talk is Earth's Infrared Background. Before we get started, I want to remind people that please hold your questions to the end of the talk. And for people who watch on YouTube, you can submit your questions to Slido. So go to slido.com and use CGD seminar. With that, Ofer, the floor is yours.
Okay, thank you, Jian. And thank you for the opportunity to present our work on the Earth infrared background. I'm particularly happy to present it at this seminar because this work was also supported by NCAR through an exploratory allocation. And I'm grateful for that and again for the opportunity to present it in this forum. So I'll explain what we mean by the Earth infrared background in the coming slides. First, starting with some motivation. So the motivation for this work comes from the tropical power spectrum, and this is our rendition of the iconic figure from Wheeler and Kiladis, which shows the tropical power spectrum as a function of the frequency in cycles per day on the ordinate and the wave number on the abscissa, where positive wave numbers correspond to easterly propagating variance and negative wave numbers correspond to westward propagating variability. And the power is also divided between symmetric and anti-symmetric components with respect to the equator. And this is, by the way, from, in this case, brightness temperature observations. Now, some of the interesting features of the power spectrum is first what we call a broad sense red spectrum, in the sense that the power decays away from the origin in both wave number and frequency. There is also what I call a symmetric bias, in the sense that in all sorts of matrix, there is more power in the symmetric component than the anti-symmetric component. And likewise, there is a westward bias, in the sense that in several matrix, there is more power in the westward propagating variability or negative zonal wave numbers. But perhaps the key feature which made this figure so iconic is the regions of enhanced variability, which are enclosed by the orange contours here and align with the dispersion relations of equatorial waves, which are marked by the black curves, and were predicted more than 30 years earlier by Matsuno in 1966. So, for example, here we have the Kelvin waves, Rossby waves, mixed Rossby gravity waves. There is also a region here of enhanced variability, which doesn't align with any of the dispersion relations. And this region is typically associated with the Mud and Julian oscillation. And the way in which these regions were derived is by estimating a background and then removing that background. And this is the background spectrum in this case, which was estimated by first averaging the symmetric and anti-symmetric components, and then applying multiple filters, smoothing filters, in an attempt to remove the quote-unquote real features from the data. So in particular, at each zonal wave number here, there are 10 successive applications of a one-to-one filter across the wave number dimension. And then in the opposite dimension, at low frequencies, there are again 10 applications of a one-to-one filter, increasing gradually to 40 applications. And this is how this background was estimated. And once you do that, you look at regions where the power is significantly above the background, which is how these regions were derived again. And so clearly, it does a good job, but there is lack of consensus in the literature in regard to how to define the background, and also a desire for a more physically motivated definition of the background, which is the motivation for this work. But I will give a disclaimer that although the motivation and the original motivation came from the tropics, we've ended up doing it on a global scale. That's why it's the Earth infrared background and not the tropical background. And in fact, the analysis I will present doesn't work that well in the tropics, as I will show later. So before I present our approach, let me present some of the other existing approaches. So by far, the most prevalent approach is the smoothing approach I've just detailed. There are also bootstrapping approaches and red background approaches, where based on the observation that the power is broad sense red, some authors have assumed a priori that the background follows a red noise process, which is empirically consistent, but it was done only in time. And so all of these approaches have their advantages and disadvantages, but in general, they are somewhat technical and statistical in nature and lacking physical motivation. The approach we will use in this work, which was pioneered by Holvey and Steckman, is stochastic modeling. And so, again, before we move on to describe the approach, let's remind ourselves what's the outgoing long wave radiation we observe, or in this case, in this animation, it's in terms of brightness temperature. So only a small fraction of the outgoing long wave radiation we see originates directly at the surface, about 15%. The vast majority, the remaining 85%, only make it out of space after interacting with greenhouse gases and clouds. And this means that it's susceptible, the OLR we observe is susceptible to the atmospheric variability, which is why we see all the interesting features, including waves, and in this animation also tropical cyclone, extratropical cyclones, baroclinic instability, and so on and so forth. But it means that the OLR we observe is also susceptible to the random variability of the atmosphere. So the idea was, let's identify a background with the random variability implied by the fluctuation dissipation principle in response to the internal variability of the atmosphere on small spatiotemporal scales. In simple words, the idea is that the noise in a system is directly related to the system's tendency to reject variations. And by the way, I'm calling it the fluctuation dissipation principle as opposed to the fluctuation dissipation theorem, which is a narrower notion that you might know from Leaf and other works. And I will say more specifically what I mean by that later on. In addition, I'm also going to assume that the background is statistically isotropic in space. Clearly, the OLR we observe is not statistically isotropic, and this is exactly why it's a useful property of the background. It amounts to saying that any anisotropy we see represents real physical features and not random variability. And that's the most basic assumption in the context of constructing a null hypothesis. Okay. So, as I said, we're going to use stochastic modeling, specifically a stochastically forced energy balance climate model, which is essentially just a diffusion equation with a stochastic source term, where tau zero here is a constant coefficient with dimension of times, and it's going to play the role of the temporal decorrelation. Lambda zero is a constant coefficient with dimension of length, and it's going to play the role of the spatial decorrelation. And there is also an amplitude epsilon zero, which enters through the forcing. And I will specify the forcing in the next slide. And so these sort of models were thoroughly studied in the context of energy balance climate models, which is where the name comes from. But these authors didn't consider the background at all. This model or a similar model was also found by Horovin and Steckman in the context of the background. From a turbulent point of view, where you can imagine that the diffusion comes from eddy-eddy flux convergence, and the linear dissipation and forcing come from eddy mean flux divergence. But in our case, we motivate the use of the model by saying that it's the simplest model of isotropic fluctuations, which has the desired properties. In particular, it's the most parsimonious model, having only three free parameters. As I said, a time scale, a length scale, and an amplitude, which is the bare minimum you need to describe spatiotemporal fluctuations. It's also the lowest order statistically isotropic model. And with proper choice of the forcing, it respects the fluctuation dissipation principle. And it links theory and observations in the sense that well-established results in climate modeling show that if the forcing in this model is white in time and statistically isotropic in space, the response has a red, broad sense red background spectrum, in the sense that the power, or a first order process in time and a second order process in space. And that's what we want, a background that is red in both time and space. So this is a broad overview of the model and the motivation for using it. And I'm now going to give one more technical slide, which is necessary to appreciate the details. So we start with the same equation as in the previous slide. It's a diffusion equation with a stochastic source term, where now the unknown is denoted by F, and the partial differentiation with respect to time is denoted by subscript T. And if we look at the corresponding equation in spectral spherical harmonic space, we get the following equation, where FLM are the spectral coefficients in spherical harmonic space of F, and likewise for the forcing S. The dot here is now the ordinary differentiation with respect to time, and the dissipation tau L is given by this expression. And this expression follows simply from the fact that the spherical harmonics are the eigenfunctions of the Laplacian in spherical coordinates with an eigenvalue of minus LL plus 1 over the radius squared. So these two terms combine to give the term here in square brackets. So what we get is what is known as a Langevin equation, which is exactly what it is. It's an equation that has deterministic damping and stochastic forcing. But it's an L-dependent Langevin equation, meaning each spherical harmonics mode here evolve independently according to L. And I should say also that the L, the total wave number of the spherical harmonics, also in a statistically isotropic model, determines the scale. So essentially what this model says is that each scale evolve independently according to the scale. And so now finally, this is our forcing. As I mentioned, we are going to assume that it's white in time, which essentially amounts to assuming that there is a scale separation between the forcing and the response, such that the forcing decorrelates much faster than the response. And it implies that it's delta correlated in time between times t prime. We will also assume that it's statistically isotropic in space, which implies that it's delta correlated in spherical harmonic space and depends at most on the total wave number L. And with that, we get a prediction for the asymptotic variance of the response at times much greater than the decorrelation time tau L. The variance is given by this expression. That's not something trivial you can do in your head, but that's an established result. And what we're going to do in the remaining of this work in 2 slides from now is we are going to first fit the model to observations to estimate the model parameters, and then construct the background and the foreground. But first, note that the scale dependence in the forcing is not arbitrary. It's exactly tau L. And this is perhaps the key point that was glossed over by earlier works, which took the forcing to be scale independent. But this is where the fluctuation dissipation principle comes in, because this is the only choice that is consistent with the fluctuation dissipation principle. So let me say what I mean by that. I'm looking at it from a broad physical sense, not in the narrow sense that is sometimes considered in atmospheric sciences. So the idea is that if you have a standard Langevin equation like so, where here W is the Wiener process, then for any choice of sigma and theta greater than 0, this equation represents a stochastic process, an Ernst and Uhlenbeck process, which decays towards an equilibrium, and the equilibrium variance is given by this expression. And the idea is that the fluctuation dissipation principle physically says that this equality has directionality, such that the equilibrium variance of the system is given, and then the noise of the system is determined accordingly also to the dissipation. So that's why we say that the system's noise is directly related to the system's tendency to reject perturbations. So for example, not every Ernst and Uhlenbeck process corresponds to physical Brownian motion. Only the subset for which the equilibrium variance is given by the Maxwell-Boltzmann distribution. In our case, we don't know the equilibrium distribution from first principles. We can only estimate it empirically. But one thing is clear, which is, except for a weird coincidence where the equilibrium variance is independent of scale, it's most likely depends on scale, and so the variance of the forcing should also depend on scale. And the dependence I showed here is the only one that works. Okay. So with that, let's look at some results. So again, this is the predicted asymptotic variance in the model, and we are going to evaluate the left-hand side from observations and fit it to the right-hand side. Specifically, we take the OLR data, we do a spherical harmonics decomposition, we compute this product, we take a time average and average also over M. And here are the results, where in orange, I'm showing the variance in the raw data, and in blue, the variance only on subannual timescales, obeying by first applying a high-pass filter with a cutoff of 1/360 days, and also applying a Welsh overlapping segment analysis with window size of 360 days and overlap of 180 days. And the thing to note about this figure is that the scaling here on the ordinate of L plus 1 is intended to make the figure show the power per scale. So you can really say that there is more power in those values of L than here and here. Okay, so you can see that at large L, that is small scales, even the raw data, the orange, can be accurately described by the energy balance climate model. So the black curve here is the best fit of the energy balance climate model. So again, at small scales, even the raw data can be described by the energy balance climate model, but on large scales, only the subannual variability can be explained by the energy balance climate model. The raw data is not far off, but there are clear deviations. For example, the uptick here at L equals 1, if you look at the grid space projection, it corresponds to a dipole moment of the annual cycle. The peak at L equals 7 is also particularly interesting in some sense because it pops up as particularly high in model simulations as well. There is also an uptick here at L equals 15 and somewhat 13, which persists also in the subannual variability, but that's a satellite artifact. So again, I think that if you look at the subannual variability, the model does a very nice job explaining the observed what is called angular variance. And so from here we get an estimate for the values of epsilon 0 and lambda 0. And as I mentioned, lambda 0 plays the role of the spatial decorrelation. In fact, it's an upper bound on the spatial decorrelation. And we should compare it to some of the relevant length scales in the data. So first, it's smaller than the Nyquist length scale, which is 500 kilometer. The lambda 0, the decorrelation, the upper bound on the decorrelation that we estimate is about 400 kilometers, substantially lower than the Nyquist length scale. And this gives us some reassurance that it's indeed random fluctuations, because it means that they decorrelate faster than the smallest resolvable wave. It's also smaller than typical Rossby deformation radius, and the deformation radius varies considerably across the globe, but I think it's fair to say that it's smaller than the typical Rossby deformation radius. And in fact, my hypothesis is that, which is something to be confirmed, hopefully, or tested, is that it represents an effective or a global Rossby deformation radius. At the very least, I think it's constrained by the Rossby deformation radius, because by the time you feel the effects of rotation, it's no longer reasonable to hope that the fluctuations are isotropic.
So, Ofer, can I ask you a question here?
Sure.
I'm unsure what this parameter A is.
Epsilon.
So, from a couple of slides before, certainly in equation 3, you've got this A, which I don't see as defined.
Sorry, it's not defined here, but I mentioned it. It's the radius of the Earth. So the eigenfunction of the Laplacian is minus LL/1 over the radius squared.
Okay, so that's a given constant.
It's the radius of the Earth.
Okay, thank you.
Okay. So sorry for that. Lambda 0 has in this slide, lambda 0 has units of length. So A is the radius of the Earth. So this term is dimensionless. I hope that answered the question. Okay, apologies for that. So with that, let's move on to the temporal power spectrum. So I haven't shown this formula yet, but it just follows from the former one by the Wiener-Henshin transformation. And we are going to do the same thing. We are going to evaluate the left-hand side from observations and fit it to the right-hand side. And so we take the spherical harmonics coefficients of the OLR that we've already evaluated and apply further Fourier analysis in time to get the frequency dependent coefficients. And here are the results, where again in orange is the raw data and in blue the sub-annual variability, so you can see clearly what was being filtered out. In particular, these four peaks correspond to the annual, semi-annual, and seasonal cycles. The uptick at omega equals 1, which is the Nyquist frequency, is folding or aliasing from higher frequency variability. There is also an uptick at omega about 0.9, which is a satellite artifact. And there is an upward inflection, which is the result of spectral leakage and finite sampling. But in general, you can see that the model does a reasonable job in explaining the sub-annual variability. And having estimated epsilon 0 and lambda 0, we can now estimate tau 0, which is about 2.3 days. And tau 0 is the upper bound on the temporal decorrelation. And that means that our background decorrelates faster than synoptic scale weather, because the limit is sometimes taken as 2 days, or the lower limit of synoptic scale weather is sometimes taken as 2 days. So the background decorrelates faster than that. The effective temporal decorrelation is given by tau L, and it decreases with increasing L, meaning it decreases with scale, meaning smaller scales decorrelate faster. And in particular, for example, at L equals 16, which correspond to the inflection point in the previous figure, and is about 1,200 kilometers, the temporal decorrelation is 28 hours. And this is interesting because it's similar to what is sometimes taken to be the limit or the transition between synoptic and mesoscale weather, which is sometimes taken as 1,000 kilometers and 24 hours. So based on this, my hypothesis is that the inflection point here is sort of an effective transition between synoptic scale on the left and mesoscale on the right. Okay. And with that, having estimated the model parameters, we can now construct the background and the foreground. So the full description of the background consists of its joint power distribution in the omega LM space. And I'm now going to show the spectra in the omega M space averaged over L, because that's the more familiar image considering the tropical power spectrum. So on the left is the, again, observed power spectrum, again, as a function of frequency on the ordinate and wave number on the abscissa, where now I'm showing the full range of wave numbers and not just between -15 and 15, as is usually done in the tropics. And in the middle here, or on the right here, I'm showing the our estimation of the background. And the thing to note here is that having estimated the model parameters, we can in principle estimate the background analytically, but instead we draw it as a random realization of an Ernst and Uhlenbeck process with the same sample size and sample rate as in observations. And this has the advantage that it accounts for the effects of finite sampling, and it provides a better basis for comparison with the analytic model. And with that, we can now form the foreground, which is obtained by, or it's evaluated as the ratio of the simple or the sample variance in the data to the sample variance in the background. And considering the log scale here, you can really think of panel C as the difference of panels A and B. The null hypothesis is that the two are the same, and the alternative hypothesis is that they are different. And this is not a trivial point because in the tropics, it was customary to look only at the significantly enhanced variability, but we argue that significantly suppressed variability is just as important. And we use bootstrapping as an hypothesis testing with a significance level of 0.001, which is what is shown here, where the white regions are the insignificant regions. And you can see that there are some interesting features here. So let's take a closer look. First, this point, these points, and this region are all satellite artifacts. And the more interesting features are these triangles, the central lobe and the side lobes. So let's start with the triangles. So these triangles correspond to gravity waves with phase speeds of between 10 and 100 meters per second. And considering the scales, they are most consistent with baroclinic Rossby waves with wavelengths of between 2,400 or 4,000 kilometers, or wave numbers 10 and 20, and periods of between 2 and 14 days. And if we compare it to the Rossby deformation radius, which is at most 1,000 kilometers but probably less, then this is why they show up, or their dispersion relation is similar to that of gravity waves. And we can really identify these regions as baroclinic Rossby waves. In addition, they are also Doppler shifted, and that's why the eastward propagating waves show up as having enhanced variability compared to the background, because in the raw data we have, or in the atmosphere, we have a westerly mean flow, and the westward propagating are suppressed compared to the background, because the background doesn't have the mean flow. Okay. Next, if we look at the central lobe, then based on the scales, it's most consistent with planetary or barotropic Rossby wave, with scales of between 5,000 and 10,000 kilometers, or wave numbers of between 4 and 8. Note again that the wave numbers on the abscissa here span the full range of wave numbers. So here we get, it's about 8. And it's suppressed compared to the background, which means that there is less planetary Rossby waves than what would exist in the background. And that's because some of the power that would otherwise go into forming planetary Rossby waves is being used to form the westerly mean. Or in other words, in the background, all we have is planetary Rossby waves. And finally, in the side lobes, scale-wise, they are most consistent with synoptic scale weather of wave numbers between 16 and 40, and again, periods of between 2 and 14 days. I forgot to say that the period is shown here on the right ordinate. There is also spectral leakage in these regions from lower frequency variability, and in these regions, there is certainly spectral leakage from higher variability frequency, or higher frequency variability. So it's difficult to say exactly what's going on here. And by now, I think that the results tend to look somewhat magical. The energy balance climate model does a perfect job explaining the angular and temporal power spectra. And so I think it helps to show some both supporting and counter examples. So first, let's show a supporting example. We've repeated the analysis for OLR data from the CMIP6 version of Wacom, and here are the results. In blue, we have a historical simulation, and in orange, a climate change simulation. And it's difficult to see here, but there are points and there is a line. The points is the model data, and the line is the best fit of the energy balance climate model. And that is as good as it gets. The energy balance climate model explains the OLR variance on sub-annual timescales in the Wacom model. And unsurprisingly, there are model biases compared to observations in terms of the estimated parameters, and the background is also sensitive to the climate state. This is the corresponding temporal power spectrum for the OLR data from Wacom. And now for a couple of counter examples. First, the surface temperature from again, the Wacom. So in general, for a wide range of temperatures, the OLR is quasi-linear in the surface temperature. And based on this, it's reasonable to hope that maybe you can use the same analysis to describe the surface temperature. And at first glance, it seems that it might be the case, but in fact, the differences here are substantial. For example, the slope here would imply a completely different dependence on the frequency and is not something that can be fixed by tuning the parameters. And that's not surprising because the quasi-linear relationship between the OLR and surface temperature is in terms of the global means, but it doesn't hold in terms of the spatiotemporal variability. And finally, as I've alluded to already, this analysis doesn't work at all in the tropics, and there are many reasons why it wouldn't. For example, the fact that the tropics are not energetically closed, and also the assumption of statistically isotropic variability is not suitable for a tropical band. And there are other reasons as well. But I now have some better understanding of how to approach the problem of generating a background spectrum in the tropics, and it's something that I'm trying to get funding for. So stay tuned for that. And with that, let me give a short summary. So we wanted to understand what's the physical origins of the background. And the idea was that let's identify it as the variability implied by the fluctuation dissipation principle in response to the internal variability of the atmosphere on small spatiotemporal scales. This gives us a quantitative model, a stochastically forced energy balance climate model, which is capable of explaining the angular and temporal power spectra on subannual timescales. With that, we get a physically based and empirically consistent null hypothesis, which in particular has the desired property that it's read in both time and space. But there are some remaining questions. In particular, the equilibrium distribution was estimated empirically, and the question is therefore what determines the equilibrium distribution, and what are the forcing and damping mechanisms that show up in the energy balance climate model. Thank you.
Thank you, Ofer, for the interesting talk. Now we have time for questions. For people in the room, you can raise your hand. And for who are watching on YouTube, go to slido.com and use CGD seminar to type in your questions. Do you have any questions in the room? Ida? I think so.
Thanks. I'm wondering if you compared your energy balance method with...
I can't hear very well.
Can you hear me now?
Yeah.
Yeah, I'm just wondering can you apply those kind of smoothing methods that you mentioned at the beginning that are used in the tropics, in the extratropics, and does your method give a different answer to those?
Well, I'm not sure. I didn't try that. As I said, I've tried to acknowledge the fact that they are simple and they work well. And let me try to go back. They are. Can you see my screen still?
No, we don't. You're not sharing anymore.
Oh, sorry. So, I mean, I'm not against the smoothing approaches. They give sound results, certainly in terms of identifying the regions of enhanced variability. But again, there was a lack of consensus in the literature regarding how to define the background in a more physical way. That's, I think, the motivation. So I'm not sure that there is real technical advantages otherwise.
Okay, thanks.
There was a question earlier about A, and I hope that it was clear or...
Oh. Yeah, I think that was clear. I had a different question. Thanks for your talk. I was wondering, so another place where the isotropy assumption maybe could get you in trouble would be at, because of land-sea contrast. And I was wondering if you'd looked at that and the spatial distribution of the suitability of the energy balance model.
What was the last part?
Well, I guess just think, so you've showed us these kind of global plots of suitability and then focused on the tropics. I was wondering if there was a way of looking at that on a more point-wise basis, where things like land-sea contrast, where you're breaking isotropy, might pop out.
Well, let me try to bring in the classical work by North. Hold on. It's something that was certainly done, not in the context of the background. So, for example, here you can see that it was done in the context of surface temperature, and you can clearly see how what you see here is correlations, and which tend to be relatively concentric at regions which are either over the continents or over the sea. But once you get to the transitions, it's no longer concentric. So this is an exercise that was done in the context of the energy balance climate models, stochastically forced energy balance climate models, not in the context of the background, but in the context of the background. It's an assumption about the null hypothesis, as I've tried to stress. Just a second. The OLR is certainly not statistically isotropic. It's far from isotropic, but this is exactly for a good assumption on the null hypothesis.
I'm sorry, yeah, could you repeat that? So you said you don't expect it to be isotropic. We just lost your audio for a moment. You don't expect it to be isotropic over land?
What I'm saying is that the OLR, I don't expect it to be isotropic at all. It's far from isotropic. It's a property of the background. It's somewhat not hypothetical, but it's a property of the background. The OLR is far from isotropic, and the background is simply a sort of a null hypothesis. And the most typical and I think reasonable assumption, or first assumption for a null hypothesis, is that the variability is isotropic. It's not that the OLR is really isotropic. I've tried to show it here in an animation, and I can show you even that even more strongly. here a necessary condition for statistical isotropy is that the variance would be uniform. And here you see the variance, and the variance is clearly non-uniform. So again, I'm not saying that the OLR is isotropic, it's just an assumption on the null hypothesis. And by the way, what other assumption would you make on the null hypothesis otherwise?
Well, since you asked, I mean, one hypothesis could be that you could represent the background with a relatively low number of orthogonal patterns, for instance. I see your point that it's a good starting point. And yeah, it'd be interesting to explore some of those ramifications.
Yeah. Okay.
More questions?
So I'll ask a question here. You started off by talking about the tropics, but then in the end you were showing global data, say from Wacom. So
Yeah.
are you a bit surprised that it works in the tropics and elsewhere, where the dynamics are very different?
So I think my point was that this analysis doesn't work in the tropics, unfortunately. It only works on a global scale, partly probably because the global scale is energetically closed, whereas the tropics are not. So I don't think that's the right approach in the tropics as it is.
Have more questions? Maybe I can ask a naive question. I think it's really interesting that you also showed the 4 times CO2. So under global warming, you have shown results for that as well. Could you please provide some physical intuition about the changes we see here?
Well, I can speculate. You see here, if you look at the blue is the estimated parameters in the historical run, and the orange is the estimated parameters in the climate change run. And you can see that there is about 10% change in epsilon 0 and lambda 0, and more of a change in the decorrelation time. And my hypothesis at the time was that some of this change is related to, okay, as I mentioned earlier in the talk, my hypothesis is that lambda 0 is at least constrained by the Rossby deformation scale, and there is good reason to believe that the Rossby deformation scale would increase with climate change, because, for example, if you look at the Brandt-Weissela frequency, and so certainly it would be consistent with greater effective Rossby deformation scale. The increase in lambda is consistent with increasing Rossby deformation scale. And then with regard to the values of epsilon 0, I don't remember what was my thought there. I do remember that we didn't have any satisfying explanation for the decorrelation time. But first, by the way, before you even start to talk about the dependence of the background on the climate state, we can. It's interesting in and of its own to think about the model biases. Why is for example, the decorrelation time so different from the observations? So I think that's an interesting work in and of itself.
Yeah, thank you. This is interesting. More questions? Okay, I don't see any question online. If not, let's thank Ofer again for the very interesting talk.
Thank you.
Okay, thank you everyone for interesting discussion.